The t-distribution is another important family of distributions, and it's defined as follows. So here we start with one random variable z, which is standard normal, another random variable y, which follows a chi-square distribution with k degrees of freedom, and z and y are independent. In that case, we say that this ratio z divided by square root of y over k follows a t-distribution. If you want to simulate random numbers from the t-distribution, you can do a standard normal. Here I have done 5 standard normal. This is the sum of squares of those, so that's chi-square with 5 degrees of freedom. So here I can do a t-distribution by doing p1 over sqrt of b12 divided by 5. So this number can be viewed as a drawing from a t-distribution with 5 degrees of freedom. We can confirm, or at least validate, that the expected value of this guy is actually 0. And the t-distribution has the property that it's a little bit more likely to get numbers further out in the tails. I just got a 287, for example, which is very rare from the normal. Let's have a look at two of them from the t family. So let's do first t1, which is which will be a random variable following a t-distribution with 1 degree of freedom. The t-distribution is sometimes called the student t, which is what Maple use. So let's do student t with 1 degree of freedom. And to compare that, let's do one more from the t family. Let's do with 5 degrees of freedom. The functional form for the PDF is fairly complex. So have a look at, for example, T2. It looks like this. The expected value of all T distributions, except for the T distribution with 1 degree of freedom, is 0. We can confirm that with T2, for example. Turns out that the expected value of t1 actually isn't defined. If you try to calculate the integral, it will actually come out to be infinite. So if I try to do mean of t1, it will probably say infinite or undefined or something. The variance is defined for t3 and upwards. That is the t-distribution with at least 3 degrees of freedom. So for example, for the one for t2, which has 5 degrees of freedom, it's 5 over 3. Actually, now that I think about it, t5 would probably be a much better name for this, since it has 5 degrees of freedom. So let's just fix that quickly. You can see that the t-distribution has a higher variance than the standard normal, which has a variance of 1. Let's then also plot the PDF of the t-distributions. So let's do plot. Well, actually, let's plot it next to the standard normal distribution. It'll be easier to do as comparison. So let's do a plot of the standard normal and the t1 distribution from -4 to 4. The blue one, this guy, that's the standard normal. This one, the red or whatever that is, that's the t-distribution with 1 degree of freedom. So what we can see is something that's kind of important, and that is that the t-distribution has a higher variance and it has fatter tails. The tails are much thicker for the t1 compared to the standard normal. If I replace this with t5, the t-distribution with 5 degrees of freedom, you'll see that the t-distribution will become much closer to the normal. Now there isn't that much of a difference between the normal and the t-distribution. The t-distribution still has a little bit fatter tails and therefore a little bit higher variance. And it turns out that if I make this degrees of freedom even higher, so let's define maybe T30 as a t-distribution with 30 degrees of freedom, and then we do 30 here. It will probably be hard to even distinguish them. That would be my guess. It's very hard to even notice the difference. And it's actually a fact that as the degrees of freedom increases, the t-distribution converges and becomes equal to the standard normal. The notation that we have for this random variable is that we say that t follows a t-distribution with k degrees of freedom, and the notation is a small t with a subscript k, which tells us the degrees of freedom. Calculating probabilities from the t-distribution is something that's also very important, and by far the most common problem as it relates to the t-distribution is the following question. I have a t-distribution and it has a given number of freedoms, degrees of freedoms, I know that. I need to find, we know that 0 is at the center. I want to find this value such that this area in the tail is equal to some pre-specified value, for example 5%, or the area in the both of the tails should be equal to some specified number, such as 5%. If it's 5% in both of the tails, then it will be 2.5% in one of the tails. So for example, if I have two tails and I want them to have 5% in total, 95% in the middle, then I can write this as follows. I want the probability of the absolute value of the t random variable. I want that to be greater than t. That means that I am in the tails, and I want this to be 5%. This is a very common problem, and we can calculate this particular value for t here using a whole array of software. This is the t. Let's see how we can do it in Excel first of all. I can use the function equal to t-distribution. This is the inverse problem because I know the probability, so I need the inv. I'm using both of the tails. Both of the tails should have a total area of 5%, so I do the two tails. If it's only one tail, then I just use the other one. Then I do the probability 5%, and I do my degrees of freedom, which I think I forgot to just specify. So let's say that k is 5, for example. So I do that 5, and that will give me the t value, which is 2.57. So this is 2.57. Then this is of course just minus 2.57 because it's symmetric. You can find the same probability using a table. So you look at degrees of freedom and we have 5, so it's this particular row, and then you look at the probability. We have 5% in both tails, that is 2.5% in each tail, so it's precisely this one. Note that this answer 2.57 would be the same if I ask for the probability in both tails to be 5% or if I ask for the probability of just the right-hand tail to be 2.5%. So the number we are looking for is right there, 2.571, and I think that's what we got from Excel as well. Yep. We can do it using Gretel. Just go to the tools, statistics table, T, 5 degrees of freedom, right tail probability. You just have to be careful with the notation. It says the right tail. So it just wants one of the tails, and we only have 0.025 in one of the tails. So that should give me the same answer, 2.57. In EViews, we do coef A equal to qt dist. We do the probability, and EViews want the probability of the left-hand tail. So you can either write here 0.025, but then EViews will give you the negative number. Or you can write 0.975, and then you get the positive value. So if we do this and show A, we have the same number, 2.57.